Okay, does everyone hear me nice and clearly?
Yep.
Brilliant, so I'll get going in that case. So I guess I could start by thanking you all very much for inviting me to speak here today. I have to confess, before a few months ago I didn't know much about your group, but having been filled in the meantime, it looks very interesting, the kind of things that you're all getting up to. And yeah, it's a pleasure for me to be here to try and share some of the work that we're doing at the University of Leicester on getting science out of meteorological satellites. So quickly to recap Earth observation science at Leicester. So our group, we have a core goal, that's to design, to build and exploit increasingly powerful satellite sensors addressing critical questions concerning the Earth's atmosphere and surface. So as well as being end users of satellite data, we also take an active interest in the design of new instruments, kind of coming up with new ideas for instruments, proof of concept studies, instrument simulations. We have some guys in our building who are involved in building these instruments, and yeah, indeed, there's been some sort of space hardware in the Earth's orbit that's originated from Leicester at some point in the last 40 years, which is quite a good record we've got going and that we hope to continue. So the group's it's multidisciplinary. We've got researchers primarily from physics backgrounds, but we also have chemists and geographers involved. And our key areas, we're interested in atmospheric composition, climate processes and trends, surface temperature, vegetation and fires, and then what I find particularly interesting is integrated observing systems, where you've got your measurements from satellites, which give you nice global coverage on a grand scale, and tying that kind of observation in with ground-based instruments, which give you high temporal resolution coverage, but just at one point, and then aircraft-based instruments, which are kind of a halfway house between the two, if you like. So we've got a lot of interest in, for example, using the ground-based instruments to validate what we're seeing in the satellites. So what I'm going to talk about today, I'm going to try and give a bit of an overview of the kind of science we're doing in the Earth Observation Group, kind of a highlights reel, if you like, from the last few years, and the kind of thing we're working on right now as well. So quite a big aspect of what we do is sea and land surface temperature. In fact, when the group first started, I think a good 15 plus years ago now, under Professor David Llewellyn-Jones, the first thing we were looking at was measuring sea surface temperature from space using the AVHRR instrument, which I'll be talking about in a second. And since then, we've moved on to try and measure land surface temperatures from space, which are a whole order of magnitude more tricky to figure out, and I'll explain why shortly. We're also, through our chemistry element, we're interested in measuring atmospheric trace gases and aerosols. We've got a group very active in monitoring air quality from space, which is something that affects everybody. And then something that I'm working on personally is mapping of greenhouse gas concentrations from space. So there's quite a wide range of things here, and this is just a subset of the kind of thing that we do. So we'll start with the sea surface and land surface temperature aspects. So the instrument that we use to try and measure these quantities is called the long track scanning radiometer. So this is a long-term series of instruments designed specifically to measure sea surface temperature. And the reason the sea surface temperature is interesting is because it's a very good indicator of the state of the Earth's climate. And the idea was you could have if you had a radiometer which was very, very well calibrated, and which was on a polar orbiting platform, you could get a global coverage of your sea surface temperature measured to a very high degree of accuracy. But as well as having global coverage and high accuracy, what's also very good about the ATSR series of instruments is we're now at a point where, having launched the first ATSR back in July 1991, we're now at a point where we can actually put together a long-term trend of the sea surface temperature, which is something that climate scientists in particular are very interested in, because it actually gives them a proper measurement to test their predictions with. So the first ATSR was launched on ERS-1 back in July 1991. Second ATSR went up in April 1995. And it was important that these two instruments were kind of overlapping in their period of observation, because so if you're going to put together a long time series, you need to be able to compare the overlapping data sets and make sure you've got the calibration correct when you're putting your time series together. And the third in the series was the AATSR, or Advanced Along Track Scanning Radiometer. That flew on board the ESA ENVISAT mission, launched in 2002, and we lost contact with that in April 2012. So the ATSR, there's basically 4 infrared channels. The ATSR2 AATSR added extra channels in the visible spectrum. This was to allow vegetation monitoring, and also gives extra information for measuring the land surface temperature. So if you think comparing measuring the sea surface with the land surface, the sea, in comparison, is a very homogeneous surface, quite a dark, kind of spectrally flat surface, so relatively straightforward to infer the temperature from your radiometric measurements. On the other hand, if you look at trying to do the land surface, you've got a very heterogeneous surface. Different surface types have different emissivities. So if you have those extra visible channels, you can use those to try and map out what surfaces you're actually looking at, which is what you need to know to figure out what temperature they're at. So the ATSR, it has a dual viewing geometry. It has, if we look at this schematic here, one field of view pointing forwards at an angle along the satellite track, and another field of view pointing in the nadir directly downwards. And by comparing the two and knowing the angle between the two, you can correct for the atmospheric absorption in between the surface and the satellite. And there's also, as I said, the instruments are very well calibrated, and we do this through 2 onboard black bodies, which are very well characterized in the lab prior to launch. And these give us 2 very well-known reference temperatures with which we can compare the radiometric measurements of the Earth. And single channel accuracy is quoted as being within 0.05 of a Kelvin with the onboard calibration. However, the actual sea surface temperature product, the accuracy is more like half a Kelvin, because you have to take into account the uncertainties from the atmospheric correction and also the cloud clearing. Obviously you can't measure the surface when there's a cloud in the way, but it's not always that obvious when you have say some thin clouds, and that could produce a bias in your measurement. So here's an example of the seasonal cycle, with the warmest part in orange, shifting up and down with the seasons. And you can actually start to pick out some of the detail in terms of the ocean currents, and that's reflected in the surface temperatures. So And here's a more recent update of that same climatology, and we're actually getting to a stage now where you're actually picking out some quite nice bits of detail, like, for example, looking along the west coast of Mexico, you can start to see in some detail some sort of the ocean currents. And this is really interesting, not just from a climate perspective, but also from an oceanographer's perspective, trying to figure out the energy balance between the ocean and the atmosphere. So one thing we can look at is anomalies from the trend. So if you kind of de-trend the data, you can use it to pick out certain climatological events. We have a nice long time series here, starting back in 1995 up to 2012. And looking at this data, you can quite clearly pick out the El Nino events for 1998. So there's a big jump in sea surface temperatures around that time. And similarly, you've got kind of a trough closer to 2007, 2008, when you have a La Nina event. And then the other thing to make note of is the very nice uncertainty that we've managed to get out of this. So doing very well here with the onboard calibrations, and a lot of work. I should acknowledge my colleague Dr. Karen Veal here in putting this time series together and really working hard to get a handle on those uncertainties and try and reduce them through improved cloud clearing, improved atmospheric correction, and so on.